will be Dongjae Lee.
Hello, I'm Dongjae Lee. Today, I will talk about Expecto extracting format specification from natural language intent. Spec-driven development is emerging now thanks to the AI. If we directly ask AI to implement code, then code quality becomes really poor and it is hard to control the model. So instead, in the spec-driven development, we write the specification first and then move on to the implementation. Then code quality improves and it is easy to control the model by modifying the specification. To enjoy this advantage, many of AI coding tools support spec-driven development workflow. Kiro and SpecKit officially support spec-driven development. Codex, Cloud Code are supporting plan mode, which is very close to spec-driven development workflow. The core assumption of spec-driven development is implementation is satisfying specification. But the problem is specification is written in natural language, not a formal language. So the only way to check it is manual inspection or simply asking an LLM again and again. So people are starting to introduce formal verification. If we use formal verification, AI implement code and proof as well. Then proof checkers check the correctness of the proof. But another problem comes along. Writing formal specification is much challenging than writing natural language specification. So Expecto address exactly this problem, and we convert by converting natural language intent into the formal specification. I will explain how Expecto works by using this coding test-like problem. Here's the problem description in natural language. First, a field is n by m grid consisting of words and empty cells, like this. If you place a bomb at x, y, all words in row x and column y are removed, like this. So the goal of the program is determine whether it is possible to remove all words with a single bomb, and if so, return the value of x and y. In this case, it is possible when bomb is placed at x2 and y5. Most of the existing methods generating formal specification from natural language intent are monolithic. It means they generate formal specification with single interaction with language model. This is the example from our baseline. Because they use monolithic method, high cognitive burden imposed on large language model, and it leads to wrong condition and duplicate cause unnecessary loop. One of the solutions to address this problem is just extract single constraint from the natural language intent. But naturally, it leads to oversimplified condition, so we cannot detect bugs in the implementation by using this specification. In contrast, Expecto generates correct and modular specification compared to the baseline. The main function of the specification is correspond to the main goal of the program, and it can be mapped to the third statement of the natural language intent. And valid pose, which checks the given coordinate is in the field, can be mapped to the left side of the first statement. And wipes all, which represents the effect of the bomb, can be mapped to the second statement of the natural language intent. And lastly, is war, which checks whether given coordinate is wall or not, can be mapped to the right side of the first statement. As you can see here, Expecto generated specification is not only correct, but also easy to map to the natural language intent because it is modular. So Expecto generates more correct specification, almost 2.8 times more correct specification compared to the baseline. And it generates easy to understand specification compared to the baseline. Here's the overview. First of all, user provide their intent in natural language. And in the spec refinement progress, it translates the natural language intent into partially formalized specification. And then spec validation validates this partial formal specification. If it is invalid, then it generates feedback and repeat the refinement loop. Otherwise, we put the valid partial formal specification into work list. And if work list has some refinement candidates, then we pop one of them and repeat the refinement loop. If work list has fully formalized specification, then now we get the formal specification. In this progress, we introduced two core ideas. First one is top-down spec synthesis, which is generates specification from high-level outline to low-level details. Second one is continuous spec validation, which checks partial specifications in the middle of top-down spec synthesis method. Let me introduce top-down spec synthesis first. From the work list, we pop the user intent, exactly same with user provides user intent. By using spec refinement tool, we translate this informally defined definition into formal definition like this. But here, undefined functions like valid posts and wipes alls are used. Instead of defining them informally at once, we define them informally. It means describe the functionality of these functions in natural language, not a formal language. By using this idea, we can reduce cognitive burden on large language model. We can reduce the cognitive burden on large language model compared to the monolithic methods. In the second iteration, same thing happens again. We pop the partially formalized specification from the work list and translate this into the formal specification. In the continuous spec validation, we can check this partially formalized specification is correct or not by using user-provided input-output example. By using this input-output example, we can ask this specification will accept this input-output example pairs by grounding this formal definition of the specification using user-provided example. Thanks to we have formal definition of valid post, so we can substitute this function call with this logical formula. And we don't have the formal definition of wipes all not now, so we encode this wipes all into uninterpreted function. And then put this logical formula into a sentence solver like G3. Unfortunately, in this case, G3 said this logical formula is unsatisfiable because of wrong boundary condition of valid post. So we generate feedback and repeat the refinement again. Now we get the corrected version of valid post. So repeat the same things again, ground specification into logical formula, and ask G3 it is satisfiable. Then now G3 said this logical formula is satisfiable, so we can move on to the next iteration. In the continuous validation, we use three different types of validators. First one is syntax and type validators. It is straightforward. And second one is logical consistency validator. It checks specification is neither tautology nor contradictory. Third one is, we seen right before slide, input-output example consistency validator. It checks two aspects of specification. First one is spec accepts correct user-provided input-output examples. And second one is reject incorrect user-provided input-output examples. Now let's move on to the experiments part. We use two different types of benchmark. First one is algorithmic problem. It consists of human eval plus And Human Plus consists of simple algorithmic tasks like implement sorting algorithm, and apps is composed of more complex algorithmic problems. And second one is real-world software benchmark. We use Defects4j, which is composed of known Java bugs in open source Java projects. And as a baseline, we use NL2PostCon, which is monolithic spec generation method using large language model. For large language model, we use GPT 4.1 mini with temperature 0.2. As well as empty solver, we use G3. Our first question is, can Expecto generate correct specification? In this experiment, we compare 3 different variants. First one comes from NL2PostCon. It trying to capture all constraints in the natural language specification. Second one is simple. It trying to capture only a single constraint from natural language description. And the last one is Expecto. Before getting into the detail, let me explain about the details of what is correct specification. First property is soundness. It is about rejecting incorrect input-output pairs. And completeness means specification accepts correct input-output pairs. So correct specification should satisfy both properties. So let's focus on the number of correct specifications. In the Human Plus, Expecto generates 1.2 times, 1.4 times more specification compared to the baseline. And surprisingly, Expecto generates 2.1 times and 2.8 times more specification in more complex benchmark apps. So in conclusion, Expecto generates the most correct specification on both benchmark, and furthermore, it generates much more correct specification in complex benchmark. Second question is about, can Expecto detect real-world bugs? In this experiment, we checked Expecto generated specification can detect known bugs in Java methods. Specifically, we provide Java document and buggy methods to Expecto and generate formal specification. Simultaneously, we run the unit test and collect input-output pairs. Here, input-output pair means that object state of corresponds Java method before executing the method and after executing the method. And put this input-output pairs to the formal specification, and we check does specification reject wrong input-output pairs. In this experiment, we use same variants and focus on the sound and complete specification. Here, Expecto generates 3 times to 7 times more sound and complete specification compared to the baseline. So we can conclude that Expecto can detect bugs using generated specification, and it means Expecto generated specification is as precise as enough precise to detect real-world bugs. So here's the summary. The problem is formal verification is really promising way, but the problem is writing formal specification is really challenging for ordinary programmers. So Expecto is the solution by converting natural language intent into formal specification. And we introduced 2 core ideas, top-down spec synthesis and continuous spec validation. Result, Expecto generates more sound and complete specification on algorithmic benchmark and real-world software benchmark as well. This is our homepage, and thank you for listening.
Hi. So I have a question about your specification and the idea of completeness. And so what prevents me from just writing the program again?
Sorry, I didn't hear.
So imagine, assuming I can solve the problem, What prevents me from just writing the program, like the actual answer, again, as a specification? Your spec language is powerful enough. So for your wall example, right, you've pretty much given me a complete mathematical description of the problem. And the only difference between that and your actual solution is that your solution is like executable or something like that, right? So why can't I, like, imagine you gave me like something powerful enough, like, the lean interface or whatever. I'll just model whatever your problem is, I'll have a complete solution, and that's my spec. How does your paradigm prevent me from doing something like that? Especially because you're talking about completeness, right? And I actually don't know what completeness means. When you have some generic, you just have some documentation, you have some code. I don't know what spec is most powerful. But given how you're evaluating completeness, I can just write this answer again and then I'll be done, right? So that's...
Theoretically, we can... I think that is not a binary concept. I think it is some kind of gradual concept. So if we have more specified specification, then we can detect more bugs in the implementation, right? So we cannot say some specification is fully specified in practice. So I think that is some kind of gradual concept. So
can I beat your benchmark by just writing the answer again? Like this one.
Yeah.
How will you do that?
Okay. Let me think about it more. And
yeah, thank you for this work. I'm Shubhendu Lahiri. I'm from Microsoft Research and one of the authors of the Andrus et al. Paper. So thank you for doing this work. It's good to see the benchmark and the techniques being used. I can address Aditya's question offline about the completeness. My question was, when we did these formal specs, they were actually Java or Python expressions, right? So what I'm curious is, and we didn't have the test-based validation because we did not assume the tests are provided. We only had the natural language, right? So that's one difference. But my question is, for the Python and Java expressions, how did you get them to Z3? Did you have a DSL to convert them to Z3? Because it's not clear how you convert arbitrary Python or Java to Z3.
Basically, we use DSL for writing specification, and for Java, because we use our own DSL, so we cannot directly apply our DSL to detect bugs in Java methods. So we serialize previous states of the object before executing the method and after executing the method into some kinds of JSON serialized states and put them into our specification.
Hi. Correct me if I'm wrong. So you're taking the natural language description, creating a high-level specification with some uninterpreted functions and trying to solve each uninterpreted function, like, right? Is that correct?
Yeah.
So I wanted to ask, let's say you have this, you're trying to solve this partial specifications, and then you're doing that one by one. What are the cases where you have tried to solve 3 partial specifications, and then you're trying to find out what the 4th function is, and then you realize that the entire spec from the beginning is incorrect, and if you had to go back and fix that from the beginning itself, and how did you solve that in case you encountered such scenarios?
Sorry, I didn't get the point.
So you're taking the natural language description, and
Yes.
the first step is getting a modular specification, with some unrealized or uninterpreted functions. And the next refinement step is you're trying to find the actual function for those uninterpreted functions.
Yes.
Now you're doing that step by step. You may have like 4 or 5 uninterpreted functions, and you're doing that step by step.
Yes.
Is what I understand. Now let's say you're done with 3 functions, and you're on the 4th function, and you realize that there is no function that satisfies your test, and you had to, and that the reason could be because your original, like the modular specification that you had, that itself could be wrong.
Yes.
And how did you go back and like figure that out, and how did you solve that?
We didn't explain. I didn't explain about the details of searching strategy. Basically, we using these kinds of tree search methods. So we sampling multiple formal definition for one informal definition. So if some path is unpromising, then we prune out that path, and we keep the searching with the promising path. Okay.
Okay, well, on that note, let us thank our speaker again and go to lunch.